We know there are such things as even numbers and odd numbers and even degree functions and odd degree functions. Let's take a moment to discuss even and odd functions. Well, what does that mean exactly? When a function is even, the following algebraic property of that function is true. We would say f evaluated at negative x is equal to f evaluated at positive x. That is the definition of what makes a function even. Now, think about that for a second. What are we saying here? We're saying that when we plug in a negative version of a number, okay, or the negative of a number, we will get the same exact output as if we plugged in the opposite input or the opposite sign input. So for example, we might say f evaluated at -1 will give me the same output as f evaluated at +1. And if a function is even, then this will be true of every input in its domain. Can you take a moment and think about an example of a function that you might consider to be even? Well, one of the most classic examples of an even function, and I'm thinking that some of you may have guessed this, is that f of x equal to x squared, or a quadratic function. Well, think about what this graph looks like. And this is a pretty easy graph to sketch. I'm just going to do a rough sketch of this parabola, a couple points there, and that is my parabola here. Not a great looking one, but you get the idea. Okay, so this is my parabola. Well, think about what's true. What is f evaluated at -1? Let me kind of zoom in on this for a second. What's f evaluated at -1? I get +1. Well, does that give me the same output as plugging in +1? Yes. Well, what about f evaluated at -2? I get +4, and that's the same output that I would get when I plug in +2. And this is going to be true. This relation that I'm seeing here between my inputs and outputs is going to be true of every single value in its domain. Now, what type of graphical relationship do you see here when it comes to even functions? We would say that even functions are symmetric, I'm going to abbreviate here, with respect to the y-axis. With respect to the y-axis. Let me just highlight the y-axis here, right? So you can kind of see that mirror symmetry over the y-axis. So functions that are symmetric with respect to the y-axis, we would say are even. Now let's shift gears and talking about odd functions. Well, what about odd functions? What do we know is true about odd functions? The following algebraic property. This time, f evaluated at -x is equal to negative f of x. So again, what does that mean? It means when I plug in, for example, something like -1, I should get the opposite output as if I were to plug in +1. Okay, so f of -1 is going to give me the opposite sign value as if I plugged in +1. Again, pause the video right now and try to think of a function that you know might be odd based on this relationship. Well, again, we would say f of f of x. An example of an odd function would be something like x cubed, right? So what would that graph look like? So something like this here, we know it's going to cross to the origin, and we're going to point up here, point down there, and this is just kind of a rough sketch of a cubic function here. All right, not super precise, but you get the idea, right? And what are we noticing here? I would say that f of -1, okay, let me zoom out here. F of -1 produces -1. F of +1 produces +1, right? So f of -1 in this case produces -1. F of +1 produces +1, right? So f of -1 gives me the same output as if I did the opposite of its positive input here. So therefore, we would see that this is an odd function here. So f evaluated at -x gives you the opposite output of evaluating at its opposite input. Wow, that sounds confusing when I just try to describe it using words, which is nice to have it written down algebraically for us. Now, as a next step, can we think about functions that might not be either even or odd, or what we would say neither, very simply? Can you think of an example that might be of a function that might be neither even or odd? Well, how about something like f of x is equal to x squared plus x, something that looks like it's a combination of an even function and an odd function. Let's take a look at what's happening here. Let's algebraically demonstrate that this function is neither even or odd. So let's evaluate this function at negative x. So when I evaluate this function at negative x, what do I get here? I get negative x, I'm going to square that, plus, I'm going to input negative x into x. And when I simplify this, I get x squared plus, or let's just say minus x. So this is f evaluated at negative x. Now, let's go through the checklist. First off, f evaluated at negative x, is it equal to f of x? And the answer is no, they are not exactly the same functions, therefore not even. Well, f evaluated at negative x, is that equal to negative f of x? In other words, does it give you the opposite sign of positive f of x? And the answer is no, therefore not odd. And since it's neither even or odd, we can say therefore, there's a symbol for therefore, it is neither even or odd. So what I've just done is an algebraic justification for why a function might not be either even or odd. And for you all, it's important to note that when I ask for an algebraic explanation for this, that we are inputting or evaluating the function at negative x. We're not just plugging in a random number. That is not an algebraic justification. By plugging in a number, we might show that for that particular point, we might be able to see some symmetry, but it is not the case for, it may not be the case, I should say, for every single value over that function's domain. One thing that I forgot to mention, now that I think about it, we said that even functions are symmetric with respect to the y-axis. It's important for me to note here, as we see the graph, that odd functions are symmetric with respect to the origin. Okay? So even functions are symmetric with respect to the y-axis. Odd functions, I know you might be tempted to say that it's symmetric with respect to the x-axis, but it's actually the origin, okay? So hopefully this was helpful in understanding a little bit more about even versus odd functions, and more importantly, how to be able to justify algebraically whether or not functions are even or odd, or neither.